Welcome to Free AI Courses, your starting point for exploring artificial intelligence. This series will guide you through neural networks, from basic concepts to building and deploying your own models. Let's embark on this exciting journey together. Neural networks are AI systems inspired by the human brain. They consist of interconnected artificial neurons that process data in layers. These networks excel at recognizing patterns, making them powerful tools for various applications like image recognition, language processing, and more. Understanding neural networks is key to unlocking modern AI's potential. Neural networks are crucial in our daily tech. They enhance social media by recommending friends, improve healthcare with disease diagnosis, aid finance and fraud detection, and power self-driving cars by recognizing patterns. Understanding them unlocks vast opportunities in tech. Let's explore how neurons, the building blocks, process inputs and decide on activation. An artificial neuron processes inputs by applying weights, adding a bias, and using an activation function to decide on activation. This mimics biological neurons firing when stimulated. Neurons are the fundamental building blocks of neural networks, crucial for understanding how these systems learn and make decisions. Neural networks are structured in layers: input, hidden, and output. The input layer receives raw data, hidden layers learn patterns, and the output layer provides the final result. Neurons in each layer connect to the next, passing information forward. This layered structure allows neural networks to process and transform data effectively, setting the stage for learning. Neural networks learn by adjusting weights and biases to minimize prediction errors. This involves making predictions, calculating errors, and using backpropagation and gradient descent to improve accuracy. Training is an iterative cycle that enhances the network's performance, allowing it to learn complex patterns and make accurate predictions. Activation functions are crucial in neural networks, determining neuron activation and introducing nonlinearity. They enable networks to learn complex patterns beyond linear relationships. Common functions include sigmoid, ReLU, and tanh, each serving different purposes. For instance, sigmoid outputs probabilities. ReLU is popular in deep learning, and tanh outputs values between 1 and 1. Imagine using a neural network to predict gender based on height and weight. By inputting these features, the network learns patterns that distinguish genders. This example shows how neural networks classify data by learning from patterns, offering a practical glimpse into their capabilities. Traditional programming requires explicit rules like, if it's cloudy, bring an umbrella. Neural networks, however, learn rules from data, adapting to complex tasks. This flexibility makes them ideal for dynamic problem solving, where traditional methods fall short. Now let's explore the different types of neural networks and their unique strengths for various applications. Different types of neural networks serve various purposes. Feed-forward networks handle simple tasks. Convolutional neural networks specialize in image processing. Recurrent neural networks manage sequential data, and deep networks learn complex patterns. Each type has unique strengths for specific applications. Neural networks are incredibly versatile, powering applications like image and speech recognition and natural language processing. They even excel in game playing, outperforming humans in complex games. These examples highlight the transformative impact and adaptability of neural networks in various fields. To get started with neural networks, all you need is a computer with internet access, Python installed, and basic math knowledge. No advanced skills are required. We'll guide you through each step. Curiosity and a willingness to experiment are your best tools for learning. Let's explore the course roadmap next. Our course roadmap includes neural network basics, building and training models, and exploring architectures like convolutional neural networks and recurrent neural networks. We'll also cover deploying models and real-world applications. Each lesson builds on the last, combining theory with practice, ensuring a comprehensive understanding of neural networks. Neural networks learn like children recognizing cats and dogs through examples and corrections. They start with guesses, adjust based on feedback, and improve over time. This learning process mirrors human learning, enhancing their ability to recognize patterns. Visualize a neural network as circles, representing neurons, connected by lines, representing weights. Data flows from input to output through hidden layers. Each neuron processes inputs and passes results forward. This structure enables complex computations and predictions, forming the backbone of how neural networks learn and make decisions. The learning process in neural networks involves several key steps. We start by initializing weights, then proceed with feed-forward to make predictions. Next, we calculate the loss to measure prediction accuracy. Through backpropagation, we adjust weights to minimize errors. This cycle repeats, refining the network's ability to make accurate predictions over time. Loss functions are crucial in training neural networks as they measure prediction errors. Common types include mean squared error for regression and cross-entropy, loss for classification. By minimizing these errors, we guide the network toward better performance, ensuring it learns effectively from the data. Optimizers are key in refining how neural networks learn. They adjust weights and biases to minimize loss, enhancing learning speed and effectiveness. Popular optimizers include stochastic gradient descent, ADAM, and RMSProp. Choosing the right optimizer is crucial for efficient training, ensuring the network learns effectively without overfitting or underfitting. Overfitting happens when a neural network memorizes training data, losing generalization. Underfitting occurs when the model is too simple to capture patterns. Techniques like regularization and dropout help balance complexity and generalization, ensuring effective neural networks. Understanding these concepts is crucial as we prepare to build our first neural network. Now let's get hands-on. We'll build a simple neural network using Python. You'll learn to define its structure, implement feed-forward, calculate loss, and update weights. Each step will be broken down for clarity and understanding. This practical approach will solidify your grasp of neural networks, preparing you for more complex models. Today we explored neural networks, their structure, learning process, and applications. This course will guide you in building, training, and deploying your own models. Stay curious, keep learning, and join us for the next lesson.